Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're dealing with this one physics problem that asks how long you should launch a rocket for in a certain case. About a week ago, got a message from a student that pretty much said, "Dr. Nighttime, I summon thee." And so I answered the call, and this was the problem that this student sent me. A rocket ship has an engine powerful enough so that when it is active, the ship has an upward acceleration of 16 meters per second squared. The rocket's engine is turned on for a liftoff period, then is shut off, leaving the rocket ship in freefall. Question is, how long should the liftoff period be for the rocket ship to reach a maximum height of 960 meters? So, before we begin with how to solve this, I'd like to give a brief overview of kind of a classification of some applied math problems, of distinguishing between a forward problem and an inverse problem. In a forward problem, you set up a situation and ask what's going to happen. So in this rocket ship question, if we had said, if I launch the rocket for this, if I turn on the engines for this many seconds, how high up will the rocket climb to? The inverse problem is, given that we observed some sort of outcome or some sort of phenomenon, what was the setup that generated it? So here we know that the rocket reached 960 meters, and we want to know how long were the engines on for in order to do that. It's typically easier to follow the logic of a forward problem than an inverse problem, because you can follow the causation. You can say, this makes this happen. But sometimes in the setup, right, we're faced with an inverse problem. One trick you can sometimes use is switching one of your knowns and your unknowns. You say, let's pretend that we actually knew the thing that we didn't know, and didn't know one of the things that we actually know, and see if we can get a sensible equation for that. And so that's the strategy that I would recommend using here. So we'll consider the forward version of this problem. If the engine is on for X seconds, and let's temporarily pretend that we knew the answer to X, we knew how many seconds the engine was on for, we'll ask, what is the height to which the rocket will ascend? So we break this up into two time periods. One is during liftoff, when the engines are on, and then one is after liftoff, when the rocket is in freefall. When engines are off, it's in freefall, and we're just waiting to see how high it'll come before coming back down. During liftoff, I'll call h1 the amount of height that it gains just during that initial liftoff period. So we use our standard displacement equation. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. Again, x is the amount of time here. We say x seconds. And so v0 equals 0 because the rocket initially stands firmly in place on the platform. And the acceleration is 16 because the problem told us it was 16. It said when the engines are on, it's going to accelerate upward with acceleration 16 meters per second squared. So we crunch in our numbers, we get h1 is equal to 8 times x squared. Then we also want to solve for v1. What's the velocity going to be once we shut off the engines? So again, we use our simple kinematic equation. We say v1 equals v0 plus a times x, where again, x is the amount of time. And we just get v1 equals 16 times x. So we know the height and the velocity after x seconds in terms of x. Then we look at what happens during freefall. Now, h2 is going to be that final height that it climbs to. And we can say, well, displacement formula again. h2 is going to be h1, the height that it reached at the beginning of the freefall portion, plus v1 times t, where t is the amount of time it's going to take between shutting off the engines and reaching its highest point. And again, v1 is the initial velocity at the start of the freefall portion, minus 4.9 t squared, right? Well, we know that gravity near the surface of the Earth has an acceleration 9.8 meters per second squared downward. So because of the 1/2 at squared, that's going to be 1/2 times negative 9.8, right? 9.8 downward, right? So we get h1 plus v1t minus 4.9t squared. And we know that h1 equals 8x squared. We know that v1 equals 16x, right? We just calculated that before. And so we just plug those in. We get h2 equals 8x squared plus 16x, 16x times t minus 4.9t squared. Next question is how much time needs to elapse before the rocket reaches its apex and is about to come back down. And there are a number of ways you could do that. You could look at the velocity equation, see where the velocity is 0. You could take the derivative and see where that's 0, because that's where it reaches a maximum. Notice you'll be getting the velocity equation out of that. The really low-tech way I just did here is we recognize this is a parabola, right? It's quadratic in terms of t. And we know our formula that the x-coordinate, or in this, the point of the vertex of a parabola follows the formula minus b over 2a, where b is the linear coefficient, right, what's in front of regular t, and a is what's in front of t squared. So we get negative 16x over negative 4.9, sorry, over 2 times negative 4.9, right? So we get that the amount of time it'll take is 16x over 9.8. Plug that into our h2 equation. Now that we know what t is for it to reach the maximum, we get 8x squared plus 256x squared over 9.8 minus 4.9 times 256x squared over 9.8 squared. Crunch all the numbers in, arithmetic happens, and we get h2 equals 21.06x squared. So, if we knew x, we would get that h2, the total height, equals 21.06 times x squared. Now we ask, well, is this easy to invert? Okay. And the answer, yeah, it's just some division and a square root. H equals 21.06 times x squared. So to isolate x, we divide by 21.06 and take the square root. X equals square root of h over 21.06. We're given that h equals 960, so x equals this square root of 960 over 21.06, and we get that x equals 6.75. Again, that's measured in seconds. And that's how you can solve this problem. Again, you pretend like you're solving the forward problem. If I knew the amount of time, how high would it go? See what equation that gets you. And once you have that relation comparing the amount of time that the engines were on to the actual height that you got, now you can use that relationship backwards. Instead of pretending that you know x and finding h, well, since we actually know h, we can just run it all in reverse and use h to solve for x. So I hope you found that useful. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.